particular, we thought about this idea. So once again, we have a mixed monothioacetal, but now in this case, the sulfur and the oxygen are both in the same ring. But the sulfur is closer. So when we generate the metallocarbene, it should selectively react with the sulfur to give the fused bicyclic sulfoniumide. And now, based on our prior work, this anomeric carbon should migrate to here. And that would give us this sort of sulfur bridge product, which we thought was interesting for two reasons. First of all, there are many, many reasonable ways to deal with this bridging sulfide. For example, we could just reduce it out with Raney nickel. But also because what that leaves behind now is not a medium-sized carbocycle, but a medium-sized oxocycle, a medium-sized ether, such as those ones I said we had difficulty forming in the original oxoniumide chemistry that I started talking about. And not only to make marine polyether ladder toxins, but even there are some simpler marine natural products that contain just a medium-sized ether, such as Lawrencin. We thought we could make Lawrencin from this known precursor, and we thought we could make this precursor rather quickly from this sulfur bridge system, which would come from this mixed monothioacetal. So that methodology was developed recently by my student Leah Kale. There's Leah. And what she did was she made these mixed monothioacetals from lactone precursors and converted the Weinreb amide into either the diazoketone or the corresponding keto ester with the diazo in between. And all of these substrates, for the most part, did exactly what we wanted. That is, we reached around, we closed the sulfoniumide, we migrated the anomeric carbon to give a sulfur bridge 7 or 8 membered ring. But there was a critical difference between the 5 to 7 and the 6 to 8. In the case of 5 to 7, we actually saw a pretty poor degree of retention by this migrating center, whereas with the 6 to 8, we typically saw a high or complete retention by the migrating center. That was actually good news because we wanted to make Lawrencin from a precursor where it was going to be necessary to migrate with retention. So this was promising. What about Lawrencin? Oh, and desulfurization works, as you would expect, with Raney nickel to give us the simple monocyclic ether. So to make Lawrencin, we make this monoprotected diol using an asymmetric alloboration reaction. So lithiation with sec-butyllithium, and then transmetallation to the bis-IPC alloborane, and then alloboration with propionaldehyde gives us this compound with high diastereo and enantioselectivity selectivity. We can take the free alcohol, acylate it with acryloyl chloride, and then that gives us a diene that we can close by ring-closing metathesis with this Grubbs-Hoveda catalyst to give this unsaturated lactone in 64% yield overall from protected mom-protected allyl alcohol. Then we can do a Michael addition of this thiol, and that's with complete facial selectivity from the top, and then using trifluoroacetic acid, cleave both the mom group and the sulfide, and then under conditions of acetal formation, we generate this. So at this point, we have these 3 centers set, which corresponds to these 3 centers. Under these conditions, we also set a 4th center, the anomeric center, and we set that with complete control for this configuration, which is the configuration that puts this in a pseudo-equatorial, well, in an equatorial orientation. And under those conditions, we also spontaneously lactonize to make the 5-membered lactone, where this carboxyl is reached around back up here to the deprotected hydroxyl that it forms when we treat this with acid. We can open up that lactone as the Weinreb amide, then acylate this hydroxyl group and half reduce the Weinreb amide down to the aldehyde. We can also just saponify this, but we actually want the aldehyde so that we can make the diazoketoester in a single step using these very interesting conditions. ethyl diazoacetate base in situ oxidant, IBX, takes us directly from the aldehyde to the diazoketo ester. And we want the diazoketo ester, it turns out, because the simple diazoketone in this case does not give us this product. So, but we had found in the model system that the dicarbonyl compound worked well. And in this case, it also worked well. So copper hexafluoroacac, 80%, we get a single diastereomer of product. We can then take out the sulfur, decarboxylate under Krapcho conditions in the microwave to give us this compound. And now to put in the olefin, Leah was able to reduce this ketone and convert it to the triflate, and under those conditions, she actually saw some elimination spontaneously, and she was able to convert the triflate then into the olefin. And this, we think, we can correlate very easily with this intermediate that Mike Crimmins reported as being 6 steps away from Lorentz. So this is where we stand. I hope to have a formal synthesis of Lorentz completed very shortly. The last thing I'll mention is Forbol, just very quickly, and just remind you that we thought we could make Forbol from this ether-bridged precursor where the angular hydroxyl would come from this bridging ether, which would mean this diazoketone would be our precursor. But we realized that there's 2 angular hydroxyls in Forbol. Maybe this angular hydroxyl could come from a different bridging ether. So this is a different strategy that would take us back to this sort of diazoketone. And Craig Stewart, who's just getting ready to defend his PhD early next year, initially explored the second route in a model system. So you can make this compound very easily. This is the work of Gary Posner, by simply adding the enolate of cyclopentanone to cyclohexene oxide, and you get a mixture of diastereomers 6-to-1 in favor of this one. Unfortunately, they are inseparable, but you can protect this secondary alcohol as the acetate, at which point they are separable. Take the major and add in the cerium enolate of ethyl acetate to give, with good selectivity, this tertiary alcohol. Deprotect the acetate, oxidize with TPAP, and that spontaneously forms the hemiketal. And then under the conditions where we would exchange in the sulfur, we could not prevent that from eliminating to the corresponding dihydrofuran. Under no conditions could we get that sulfur in there. So we just decided to try to use this dihydrofuran by doing a dihydroxylation, which was completely facially selective to give us the diol, which we then tied up as a benzylidine acetal, unfortunately as a 1.5-to-1 mixture of benzylidine anomers. Then saponification of the ester, conversion to the diazoketone in poor yield gave us both diastereomers of diastereomeric at the anomeric center of this substrate. And each of these could be reacted separately. This diastereomer, where the phenyl group is kind of pointing out away from the action, rearranges by way of this very elaborate polycyclic ylide to give us this product.